I would like to discuss this problem from the point of view of Gauss law. This is a problem that we have solved before. We have solved it in chapter 21. It's basically two infinite planes which are parallel to each other, and they have surface charge densities plus sigma and minus sigma. And so we have discussed it before, but I would like to discuss it again from the point of view of Gauss law. And how can we find the electric field produced by this arrangement by using the Gauss law? All right, so let's look at this problem from the side view. In the side view, the planes basically look like infinite lines. Let's use this point of view for the discussions, and then let us see how why we cannot claim that this problem has the complete planar symmetry. So it has the usual translational symmetry, obviously, along this direction. If I translate these charges along, let's say that this is the z-axis again. So the xy plane is basically parallel to these planes. So if I translate these planes on the xy plane, the charge distribution doesn't change. So it has the translation symmetry. However, it doesn't have the reflection symmetry. So if I change the z with minus c, in that case, this negative charge will basically be moved in here. So the signs of the charges is going to change under this reflection. And because of that, this doesn't have reflection symmetry. And which means that if we don't have the reflection symmetry, we cannot use the Gauss law directly. The problem is that, I mean, in the problems with planar symmetry, somehow we knew that if I have a point in here and I have an electric field in here, I knew that there's a corresponding point in here where the electric field is equal and opposite on the other side. If I don't have the left-right symmetry, I cannot claim this. And so as a result, I cannot choose a proper Gaussian surface which will enable me to use this kind of an argument. Okay, so as a result, because of the absence of that argument, I cannot solve these kind of problems like that. So as a result, I cannot apply them directly. What I can do is to use the superposition principle. Basically, forget about one of these planes, just consider only one of the planes. Well, this has planar symmetry now. It also has the left-right symmetry. Just compute the electric field for that one, and then remove this one, and then just compute the electric field for the other one, and then add them up. Right? This is the usual superposition principle, and this is how we solve that problem. Still, we can apply the techniques of the the Gauss law in here. So if I choose a Gaussian surface like that, for example, so in that case, I cannot talk about any kind of a symmetry in here. In that case, if I know for example, the electric field outside in here, then by using the Gauss law, I can compute this electric field on that part of the surface. And somehow, if I can find the electric field outside, I can compute this. So at least for that problem, I know that the electric field outside is 0. But in any case, I mean, if I know that, therefore, I can easily apply the Gauss law here. So the only problem appears in here is to find the electric field, in at least one of these regions. Once I find that, then I can use the Gauss law. Okay, so I'm just going to use an argument in here. So this is actually, sorry, I'm just going to undo and erase everything in here, right? So the argument that we are going to use in here is something like this. So first of all, suppose that this negative plate is not in here, in which case I can say that, sorry, the electric field at this point and the electric field at that point, these are equal and opposite because they are produced by this infinite positive plane, and we have the left-right symmetry, and we also know that for infinite planes, the electric field does not depend on that distance. So as a result, these two electric fields are equal and opposite. Also, I have just erased this thing and then considered that plane. So just, I'm kind of applying the superposition principle in here too, but I'm using the symmetry argument in that case. So suppose that this plane doesn't exist and I consider only that plane. In that case too, this is going to produce an electric field in here, which is going to be satisfying this symmetry condition too. So this then implies that if I consider both of these planes, in that case, whatever the electric field I have in here, I should have an equal and opposite amount of electric field on the other side. Right? This is in general true for any kind of a planar charge distribution. So these charges actually do not matter. Let me just give an example like that. So suppose that we have like these three planes. So suppose that this is a charge density plus 3 sigma, that's minus sigma, and that's let's say minus 7 sigma. So in that case too, if I have an electric field in here, E1 let's say, I can argue that the electric field in here is also equal to E1 but in the opposite direction. And that's basically the argument that I'm using. Okay, so with this additional information, then I can use the Gauss law. What I do is this. I choose a Gaussian surface like that. As a cylinder, one base is in here. It passes from this point. The other base is in here. It passes from that point. I'm also using the fact that this electric field in here, at least electric field on that whole region doesn't depend on the precise location of that region. So as a result, there are these additional information that I'm using in here. Okay, so what I do is this. Sorry about this. I also, let me show that the area in here is equal to A. So I write down Gauss law. So the flux integral of the electric field is equal to enclosed charge divided by epsilon 0. So if I apply it like that, in that case, on the right I am going to get, I again divide this surface integral into these three parts. An integral over the left base. So this integration is not going to change. Side surface and a right base. Okay, so the side surface integral is always equal to 0. On the right base, the integral is E1 times A. On the left base, it is also equal to E1 times A. And let's remember that I'm using the fact that the surface normals are also at these two bases are equal and opposite, right? And because of that, I get the same value in here. And so therefore, this flux integral is 2E1 times A. What about the enclosed charge? Well, enclosed charge is in, I'm going to use a green color for that. Enclosed charges, part of the enclosed charge is in here. So this enclosed charge has a value of plus sigma times the area. A is the base area. And there's also that enclosed charge in here, but this time this is minus sigma A. So these two are the enclosed charges. So therefore the right hand side is sigma A and then minus sigma A added up divided by epsilon 0, which gives us 0. So therefore the outside electric field is equal to 0. So I mean, for the capacitor arrangement, I know that the electric field outside is 0 in these two regions. This is one way of showing it. But if, I mean, this is just an artifact of the fact that these two charges are equal and opposite. In this kind of a situation, for example, when some of these surface charge densities is not 0, in that case, the electric field in here would be non-zero. All right, so you are going to compute a value for that. In any case, let's go back to that problem. All right, so this is the problem in here. So I know that the electric field in this left region is 0, right region is 0. And I would like to compute the electric field in here. How do I compute this? There are these two methods. So one is to choose a Gaussian surface like that, in the shape of a cylinder again, but the right base is passing through that point and the left base is on the left side. Or I can choose a Gaussian surface like that, where the left base is passing through that point and the right base is on the right side, in which case the electric field is like that. Okay, so again, I'm going to use capital A for the surface base area. So I'm just going to call this as, this is the Gaussian surface 1, this is the Gaussian surface 2. I'm going to solve the problem by using each of these Gaussian surfaces. At the end, we are going to see that we get the same result. So you don't have to do this, but I'm going to show you how you're going to get the same result from the second, from the other Gauss choice as well. So again, for choice 1, I have this integral, E dot dA, and that's equal to the enclosed charge divided by epsilon 0. The integral is divided into these 3 pieces. So there's a left base side surface integral and a right base integral. So let's just write it down like that. On the left base, first of all, let's start with the side surface. So side surface integral is always equal to 0 because the electric field is parallel to the side surface. So therefore, there's no flux. So the electric field in here is not going to produce any flux. On the left base, I'm talking about this surface in here. On the left base, there is no electric field. So because of that, the left base, there is no flux from the left base. On the right base, I can see that at least I'm just looking at that arrow in here. E is the component of the electric field along that arrow. So I think that's important to recognize. But let's suppose that E is positive. Probably it is. Surface normal is along the same direction. So therefore, the electric flux in here is positive. So let me write plus E times A. If E is positive, then the flux would be positive. So by just looking at these directions, I can also decide on the sign. What about the enclosed charge? Well, only this charge is enclosed in here. And so therefore, the enclosed charge is plus sigma times the base area. And so the areas cancel. So as a result, we find the electric field to be equal to sigma divided by epsilon 0. Okay. So that's basically the answer to the problem. But let's solve the problem from this by using the other surface. So I think I'm going to make a copy of that picture. And I'm going to move somewhere else. All right. And yeah, I can now use the second one in here. So forget about this this picture in here. So I'm going to use the second choice. Hopefully we are going to find the same result. So so that's a choice 2. So the flux integral is an integral over the left base side surface plus right base okay. Again, side surface contribution is 0. Right surface's contribution is again 0 because the electric field outside is 0. What's the contribution of the left base? I need to express it in terms of this electric field. Here the surface normal is outward, but the electric field is pointing inward, which means the flux is entering. But when we are writing down the Gauss law, we say that we always compute the electric fields, the electric flux leaving out of the Gaussian surface. So here it is entering in, so therefore this is negative minus E multiplied with the area. So the flux is negative in here because the electric field line is basically entering into the surface, crossing the surface and entering inside. What about the right hand side? Well, we have enclosed charge in here. So that's the enclosed charge. How much charge is there? Well, it is surface charge density is minus sigma. And so I need to multiply this with the area. So that means on here we have the surface charge density minus sigma, and the area is A. So that's the enclosed charge. We divide by epsilon 0. And so therefore from here we find the electric field equal to sigma divided by epsilon 0. All right, so that's basically the solution of the problem. Let's repeat again, right? This is the capacitor arrangement. So if I have two parallel plates with positive surface charge density positive sigma and surface charge density minus sigma in here, in that case, I find that the electric field is 0 outside, exactly 0, and inside the electric field is field lines are basically lines drawn from the positive plate to the negative plate, where the electric field has the uniform value of sigma divided by epsilon 0.